Well, good afternoon and welcome everyone. Thank you for joining us today for a two-panel event, Small Satellites, Big Missions, the implications of the growing small satellite market for launch and key applications. Our first panel is going to look at the question of applications, missions for small satellites. Second panel will cover the transportation launch side of the equation. I'm going to begin, as we always do, with our safety brief, which is to say, if for any reason we had to leave this room due to a safety issue, I would be your safety officer and would give you directions either to go out the way you came in or, if necessary, to go out the back. But that is very unlikely to happen. But if something were to happen, look to me for direction, and I'll try not to panic. I also want to recognize the sponsor for today's event, which we always do, and we were able to put this together as a result of support from Strata Launch Systems, so we really appreciate their support. I'm not going to get too deep into the substance of this because you've got really smart people, much smarter than me, who are going to do that on these two panels, but I want to set the scene just a little bit. I think there's been a lot of discussion about small satellites and what they can do for the country, for the economy, also potentially for defense. We really want to drill down on that, not just on, sort of the out there possibilities or the far edge possibilities, but also to explore concretely in the near term what specific things can small satellites deliver to the market and potentially to the Department of Defense and to national security applications, which are always a focus here at CSIS. Historically, the government has been deeply involved in space, deeply involved in launch, deeply involved in space layers, but it has historically done that often by owning them and by launching its own systems, by building its own systems, or working with industry to build its own defined systems. And we appear to be going towards a new paradigm where the commercial sector, where industry is doing more of its own development for its own purposes. And that seems to be particularly true in the small satellite space. That's a niche area where the energy is much more so on the private sector side. But that doesn't mean that there are significant uses in defense for where that's going. How might the Department of Defense access that? Historically, as I mentioned, it hasn't always purchased space services. The government has tended to approach space more as an organic domain for its own activity. How do you use all these products that are out there on the market? How do you access them if they're coming from non-traditional sources, not the usual players, which hasn't always been DoD's strength? How might you use these services to add resiliency to DoD's own systems, to complement the organic space infrastructure? And oh, by the way, what do you do with all this data? One of the major outputs of all these things, massive volumes of data. How do you handle that? So those are just a few of the issues. I'm sure our panelists are going to surface, quite a few more. You will suffer sitting out there listening. But without any more suffering listening to me, I'm going to ask Todd Harrison, my colleague here at CSIS, to come forward. He's going to moderate the first panel.
While I'm talking, I'm going to ask all the panelists to go ahead and come up on stage and take their seats. And I want to go quickly to a chart we want to throw up here on the screen that talks about the increase in the small satellite market that's projected for the near future. So I want to thank our folks at Avocent for giving us access to this data. They maintain a database. And what you can see here on this chart, the lighter gray section there is the projected growth and the number of small satellites launched every year. I started early in my career working in the aerospace industry at a small satellite company. That's actually where I met Aaron. We both worked at AeroAstro back in the day. We won't say how long ago that was, but we were probably in middle school at the time. Back then, that was a time when we also saw a lot of hope, a lot of big plans for building small satellite constellations. And it looked for a time like this sector of the industry is really going to boom. That didn't happen for a lot of different reasons. And so you can see where we've been for the past several years is fairly flat in terms of the satellite market. We've seen some growth, some uptick here in very recent years. But a lot of the big growth you see out there in the future, it's still in the future. And so that's what people are struggling with now, is this real? Is it going to happen? And so that's what we want to talk about on the panel today. And so I'm going to just go down the line here and ask each of the panelists to give some introductory remarks, and then we'll have a Q&A session. We'll open it up for questions from the audience. So as you're hearing the discussion, please, if you've got a question, take a note, and we'll give you a chance to ask at the end. And so here, I'm going to transition to sitting down here. All right, so I'll start to my left here with Dr. Bill Jeffries, CEO of SRI International. He previously served as the director of the National Institutes for Standards and Technology, NIST, back in the Bush administration. Also served as a deputy director of the Advanced Technology Office at DARPA. So a lot of great experience. And so, Bill, why don't we start with you?
Well, thank you very much, and I'd like to thank CSIS and the sponsors for hosting today. Hopefully it will be an informative and fun day. So as I was thinking about this, it struck me that if you allow me a lot of liberty with history for a second, we could actually view this October as the 60th anniversary of the first small sat launch, because that was when Sputnik 1 was launched. Now, Sputnik 1 was about the size of a beach ball, okay? It had a whopping transmit power of 1 watt, okay? And think of how much that cost to build and launch that in those days. Now, in the decades since then, we've gone down a path where we've been spending a lot of resources in building much more capable systems. Those much more capable systems mean much bigger, much heavier, and typically much longer time on orbit, as well as longer time to build and design. Well, what's happened over the last decade or so, although it doesn't necessarily show up as much on that chart, is a shift towards being able to build really capable systems in really small volumes. And if I go back to the Sputnik for a second, if you put that into today's language, Sputnik was about a 100U configuration, and it was a 1 watt beacon. Think of what we could put into orbit today at 100U type of configuration. So the technology has definitely opened up a whole new paradigm for what we can do. So I tried to think about some of the ways that this could, as we look towards the future, really start to impact both the national security as well as the civilian side. And so there's a couple areas where I think small sats may play a huge role. One is that the lower barrier to entry really opens up a whole new avenue for training the next generation of space engineers. I remember many, many years ago when I was in the White House at OSTP, AIAA had published a wonderful report that talked about the number of aircraft designs that a typical aerospace engineer would work on in their lifetime. And in the 1950s, it was about a dozen or 15, dropping down to about 1 right now because the time frame of building those systems was so much longer. And the quality of the engineering experience by not being able to build a little, test a little, was a detriment. Well, small sats changes that whole paradigm for space. It allows engineers the opportunity to actually build a little, test a little, try out new concepts, really risky experiments, things like on-orbit servicing, refueling, space manufacturing, all the kinds of things that we would love to have that would also benefit national security, but it's too risky to do in the traditional way of doing that. There's also, it's opening up whole new avenues for the commercial side. There's a number of startups. Venture capital has now suddenly recognized that small sats exist, and they're starting to get interested in how they can play in space. So you're going to see this wave of, from Silicon Valley and others, of now playing more and more into space. That will manifest itself in a number of ways. Probably the earliest, as shown up there, is going to be mostly communication satellites and also additional imagery satellites. So what does that mean for both national security and for the civilian side? when you've got revisit times, for example, of imagery way down. Okay, how can NGOs, for example, use that to help predict where the next famine will be or where the next migration will be, where they may be able to get in early and help? And right now, that access is a lot more difficult. Governments can start to think about architectures in a different way. Rather than one single giant Battlestar Galactica, can you disaggregate them? Can you, if you don't need simultaneity in the operations, perhaps a disaggregated architecture actually becomes more robust. And so there's that kind of options. Launch on demand, right? We've been talking about this for, I don't know, at least 20 years since I've been in the Beltway, of getting launch on demand. That not only provides the Department of Defense a robustness in terms of being able to replace systems that may be lost on orbit, it allows a surge capacity. And that surge capacity can allow for new geographical regions that weren't necessarily planned for in advance, or it can provide new capabilities. And the last thing that I want to talk about is something that we don't always mention when we talk about small sats, which is the ability to have a huge number, a constellation of hundreds of systems up there that can exploit new phenomenology. If you've got something that you're looking at that is highly dynamic, that you need in situ measurements, and you want continuous global coverage, that is something that the traditional large systems cannot do. So let me give you an analogy. If you wanted to forecast what the weather is going to be like in Washington, D.C. tomorrow, and the only thing you had was a single thermometer in Kansas City, how good do you think that would be? Right? There is a number of systems in the space environment that are highly dynamic, that you want high temporal coverage, and that you want a lot of spatial coverage. Space weather, radiation environment, looking at subtle changes in the Earth's magnetic field, looking at 3D continuous structure of the Earth's atmosphere, looking at mixing. Those are all deep science questions that we don't actually have the capability of addressing today. And then move that to something like the Jovian system, and it gets much more complex. So I'm actually very, very bullish that as small sats continue to develop and the launch capability, particularly getting very low-cost launch access, that we're going to really be able to rewrite some of the scientific knowledge of what we've got of the Earth's atmosphere and the planetary systems around us. So with that, I'll turn it over.
All right. And so next up, I want to turn to Colonel Butow, who is the West Coast Military Lead for the Defense Innovation Unit Experimental, which is more commonly known as DIUx, member of the California Air National Guard, correct? And also previously served as the CENTCOM Deputy Director for Joint Search and Rescue Center during Operation Enduring Freedom. And so, Colonel, I want to go to you and see if you can give us some insights into what's DIUx doing in small space, and what can small satellites do for the military?
Sure. Well, first, for those not familiar, DIUx was created by the former Secretary of Defense, Ash Carter, in order to permit the DoD to reach out and engage with non-traditional innovators. So non-traditional just mean our traditional innovators are those within the defense industrial base. And there's a number of technical areas where the advances are just exploding in the commercial sector, as our moderator brought up earlier, where we have some, usually our tie into those areas is through the labs. But the maturity of those things into our normal programs of record take time. And I want to caveat my remarks by first saying that big sats are very important to us, right? So our exquisite systems, our national technical means, there's no replacing them. They are absolutely essential for what they do and what they provide. So our interest in small sats is really not that, but it's the convergence of a couple of different innovations, if you will. One is obviously, actually the first CubeSat was actually just a mobile phone, right? In I think it was a 1U bus, and just to say, hey, what if we apply this technology? And what it showed is well, mobile electronics operate just fine in that environment with a little bit of engineering. But it's the combination of those low-cost sensors with the advanced analytics that are emerging right now. And also, as the next panel will discuss, the advent of more frequent access to space through commercial means and diversified options, ranging from rideshare to being able to put things precisely where they need to be, hopefully in short order. So normally when the DoD does business with the commercial sector, we go through something called FedBizOps, which if you're a high-tech company in Silicon Valley, Boston, or any of our ecosystems, they don't even know what that is. So we have to be boots on the ground out in these technology sectors, and then relying on our relationships through the labs, such as SRI and others, to find out who these people are, what they're doing, and enable them to prototype their commercial capabilities with the idea that we want to assess their ability to add to our understanding of the environment. So we are specifically right now, our first space project, we're funding commercial synthetic aperture radar microsatellites, and it's a competitive program. The wonderful thing about it is when we started, there were 0 U.S. commercial providers of SAR, and so we're funding that. We're funding analytics companies to work with them, with the idea that we're launching a capability to look at patterns of life. What are those things that could serve as peacetime early indications and warnings of things that we need to know about? And the wonderful thing with that is it's the ultimate big data problem, because we need to ingest a lot of data from everywhere, not just focusing on specific targets.
So next we'll turn to Dr. Bhavya Lal, who's a research staff member at the Science and Technology Policy Institute within the Institute for Defense Analysis. And I happen to know that she has been recently doing work looking at trends in the small sat market space. And so, Bhavya, I want to turn to you and see what are you finding that's going on in the industry?
Thanks, Todd. So there was a Star Trek episode, or original series, where they run into this species who don't understand what children are. So they're trying all different ways to explain what a child is, and then Captain Kirk just gets frustrated and says, they're like humans, only smaller. So, it seems to me that for a lot of people, a small sat is like a traditional sat, only smaller, and it costs less. So it just seems like such a great idea. Why would we pay less? But so I want to make 5 points in the 5 minutes that I have, and that's my first one. That small sats are a fundamentally different entity. Yes, they're smaller, they may cost less, but they also offer a different set of capabilities. And I think both Bill and Colonel Butow talked about some of that. And I think my second point is that unlike the exquisite NTMs, small sats are just a different value proposition. Sometimes you don't need a Ferrari to get to where you want to go to work. A Ford Focus is good enough. And I think in some ways, small sats are that. Whether you're doing Earth observation or satellite communication, or even things like detecting incoming asteroids or discovering exoplanets. They offer a capability that maybe not at the same level, but it's something that is in the interstitials. And if I had to try to kind of put into buckets the application areas that my preceding panelist talked about, sort of there is a risk-taking bucket that you can take more risks. But they are cheaper, so you can do different things. You can experiment. The second bucket I would call speed. So the Mars rover, the Curiosity, had a 1 megapixel camera, and the reason for that was the design was frozen 10 years ahead of time. Now, Canon just came out with a 250 megapixel camera. So if you can refresh your satellites more often, not, maybe even every few months, you can put a lot more capability because you can move much farther with Moore's law, as I think Bill talked about. And the third piece is new capability, things that we just couldn't do before. So expendable platforms, you can do research in very low Earth orbit. You couldn't put spacecraft there because they just degraded too quickly. Or, Bill mentioned constellation, simultaneous multi-point data collection, secondary lines of sight. You can see, you can have sister spacecraft that go with the mothership. So lots of really interesting new capabilities that you now have because you have small sats. So that was sort of my second point. My third point is that in some cases, small sats may seem to offer much less capability. Planet Lab resolution is 3 to 5 meters. But the interesting thing about small sats, like any other disruptive innovation, is they're moving relentlessly up the capability curve. So taking an example of attitude control, measure as pointing accuracy. We improved 2 orders of magnitude in 5 years, and the improvements are much faster than expected. So we would be another 2 orders of magnitude in the next year or 2, and that's really something. My fourth point is, while currently Earth observation and remote sensing and communication are sort of the initial killer apps of small sats, and they do comprise most of the activity today, the really interesting stuff is in other applications such as low-cost RPO services or space-based situation awareness. Things like space-based space situation awareness, things that we just couldn't do with smaller spacecraft. In theory, just with Earth observation and communication satellites, you can even close the case for the commercialization of space, and even potentially, the case for a launch. But a lot of it remains to be seen, which brings me to my, well, I'll come back to that. My next point was, while it seems that small sat innovation is a very US-centric phenomenon, in our research we found that there's 70 countries in one way or the other involved in the small sat world, and it's a very international community. So, for example, Danish company GomSpace, they have their software-defined radio is for one of the best values in the community, or the Finnish company ISI, which is developing a small sat SAR platform. So I think it will take some effort to keep the cutting edge in the United States. We cannot take it for granted. And the last point I wanted to make, since I'm a little bit over my 5 minutes, is that a lot of the capabilities I'm talking about are in the future. And I think we really do need to remember that we don't get overtaken by the hype. And just a few days ago, there was this article that talked about how Rocket Lab, which is a small sat launcher, has had one launch, not the ideal orbit. They're valued at $1 billion. Arianespace, which is, it's been around forever, 80 some launches without any flaws, it's valued at 500 million. So there's a lot of really, there's excitement in the community, which I think we need to capture, but we just do need to know that investment is a sign not of success of the sector, it's a sign of interest in the sector. And we should just keep that in the back of our mind. And so the point being, while there's a lot of potential to change the space domain, let's not count our chickens ahead of time. There's a role for government here, and I guess in the rest of the discussion, maybe we can talk about, what that role is. Thanks.
And so, last up on our panel for opening comments is Aaron Rogers, who's Program Manager for Disruptive Space Missions at the Johns Hopkins Applied Physics Laboratory. And so, Aaron, want to go to you and get your take on what can small satellites do, and what's the disruptive change that's coming.
Sure, thank you. One of the challenges of being the last on the panel is to adjust in real time to all the remarks said by your colleagues. And so I share a lot of their common sentiments and thank them for setting the stage for some of my remarks. So I'd like to try to add something new to the conversation, which is what is the right size of a small satellite? And I think that question has been asked by lots of people for so many years. And I think, historically speaking, it's driven a lot by launch and space access. And even going back a few years, the only way to get to space if you weren't buying a dedicated ride was, first entry was to go as a CubeSat, a 3U CubeSat. And so fast forward to present, we're seeing a lot more access to space and form factors much larger than 3Us, now 6Us, 12Us, conversations of things much larger than that. We're seeing these new commercial rideshare options, dedicated commercial rideshare programs offered. And so that's in the rideshare community. We also have a panel to follow that will talk about access to space for dedicated low-cost launch that can provide also measures of schedule continuity and confirmation, as well as resilience and responsiveness that comes through dedicated launch. So there's excitement about space access now, and that's really important. The The other thing is you think about sort of the size of satellites is once you decouple the launch access component is what's the mission need? And the first thing people think about is, what's an aperture we need for a picture of the resolution of a ground? What's the antennas and elements of the payload accommodations? And once you can decouple the launch opportunities and now let yourself to think more what's driven by the mission need, you can think about larger form factors. And we actually looked at this a few years ago in a study and found there was sort of a nice gap class of missions, which we sort of proposed to be called Express class, and that was somewhere between a 3U and a 6U and an ESPA or steamer trunk size satellite system. And that was one that was postured to take better advantage of rideshare opportunities, but also give more physical payload accommodation provisions. Size, weight, and power, namely to operate the payloads, the CONOPS and duty cycles of those missions, as well as most at the cost point of view, take advantage of commercial technology off the shelf more readily. When you go to small form factors, 3U CubeSats, you oftentimes need to spend a lot of money to miniaturize and package your system as opposed to using what exists and what's got a high maturity form factor. And so with larger form factors now moving forward, we're seeing the opportunity to take advantage of those new cutting edge integrated subsystems much more readily. I'll point out that traditional small satellite systems tend to have a density of about that of water, a gram per cubic centimeter. And we're seeing new small sats being built right now that are more 50 to 70% greater than that. And so we're seeing highly integrated electronics taking advantage of commercial packaging techniques and other state-of-the-art technologies to really drive technology up, as well as to put that in very small form factors. Of course, driving all this is a desire to do, as was noted, field constellations and heterogeneous architectures to support, lower cost, high performance, higher temporal and spatial resolution and diversity and global access. And so all that sort of coming together as technology is marrying with launch access and the application space is coming together. And so we see a very good confluence that the government and the commercial sector is really drawing upon now. I will point out just a few challenges that we still see ahead of us, and it was noted by some of my panelists, is that this confirmation that the proffered performance and quality of some of these the new offerings has not yet been realized. There's still quite a few that are in sort of early stage pitch mode and have actions and plans to get to orbit and demonstrate themselves, but there's still rubber meets the road in that respect. And that takes typically a couple years beyond that Series A round of funding to see those demonstrations occur. Some notable examples that I can think of in recent times was some of the hyperspectral imagery missions being proffered by Boeing and by OmniEarth, and those programs don't exist as flight programs. They moved into analytics, but not the barrier to entry with the satellites themselves. Also, the notion of architectural integration is still a big issue. How do you take the commercially produced data and knowledge products and bring those into the systems that the government or other consumers are used to using? There are good proof positives that this can be done, and recent data buys from NGA for Planet and GPS radar occultation data by NOAA are clear intentions of this desire. Lastly, the notion of pragmatic balance between cost, schedule, and risk as it pertains to system reliability and availability. As we try to seek and utilize the latest cutting-edge technologies in the market, we have to recognize that there's not going to be lots of maturity data or other information to indicate how well that performance will survive in space, and so we have to balance and temper sort of expectations with regards to outages or mortality, which can be in opposition to traditional norms. I had 4 items, which I should say the last one is sort of architectural resiliency and timeliness issues that are driven by ground network access, and how do we build robust networks that we can use and access. So with that, I'll conclude my remarks. Thank you.
Okay, well, the first question, I want to go down the line here and ask each of you to comment on this idea of resiliency, picking up on what Aaron was talking about there at the end. The U.S. military and the Air Force in particular have talked a lot about the need to improve the resilience of our space capabilities in recent years, and part of this is because we're seeing proliferation of threats around the world. But you look at our military satellite constellations, and for the most part, our constellations have a small number of large satellites. And you look at this most recent budget request, and there's beginning the early stages of follow-on programs for advanced DHF and for SIBRs, for missile warning and protected comms. And we appear to be continuing to do the same thing, buying a small number of large, highly aggregated, very expensive satellites that are going to take a very long time to build and put onto orbit. How can small satellites help improve resiliency for military space systems? Do you want to start?
Sure. So thank you. So I think there are a number of ways that small sats will ultimately help the resiliency. I'd like to start off by echoing something that Bobby has said, that a lot of this is in the future. And as one builds a robust architecture and a resilient architecture, it also has to have relatively low risk when it goes up. And so what I think you would see is a time shift where initially it's going to continue, the constellations are going to continue looking like they look, but over time, as the small sat capability becomes a reality, I think you'll start to see the architecture being able to blend in, and either you get a heterogeneous system from day one, or you get the ability to quickly replace or surge on a time scale that's much shorter than the traditional constellations to supplement the existing things. But again, it's going to be sort of proof in the pudding first, and I think we've seen that already with things like imagery, where national security has adopted some commercial imagery to supplement the capabilities of existing systems. But it's got to be proven to be real before it can go operational.
As tempting it is to talk about strategic resiliency, I'm going to actually talk instead about industrial resiliency, because the one thing I've observed firsthand since being at DIUx, I mean, we have some great companies that will work on developing our cutting edge technology. It takes a while for these satellites to get employed, and then they last forever. And what do you do with these guys in the meantime? And a lot of these companies, they get fewer and fewer by the day, and you don't have that churn so that you have the mentors training the next generation of engineers. So that alone is there's not a lot of resilience in that model, and I think we've seen gaps just in space over the 60 years that was talked about earlier. So the nice thing is when you bring in these commercial solutions, just as was mentioned earlier, you could take more risk, you can experiment, you can do things that you can't do with these large programs of record, and at the same time you can be seeding the technology. We're actually working on a battery project right now, because the lithium-ion batteries for that small form factor just ain't going to cut it. And and if you're going to incorporate the latest, greatest battery technology on our expensive systems, you want to build some space heritage first. The commercial options are the best way to do that, because it allows the labs to get into space not just fast, but on a recurring basis. So we can do agile experimentation and development without really sacrificing a lot. And then those technologies will find their way over into the other side, but also keep a lot of smart people gainfully employed between the real big projects that they do every 20 years or so.
So without repeating anything that Bill or Colonel Butow said, I think one thing we should point out is that you mentioned the large number of launches coming up. 80% of these are commercial. So I think we can assume that if there's any resiliency expectations, they would be from commercial industry. And that is where it actually gets interesting and complicated, because a lot of the companies that we looked at aren't using radiation hardened parts. They're using cheap COTS parts. They are not their standards for cybersecurity aren't as high as our traditional NTMs or even non-NTMs are used to. They're proposing commercial-oriented approaches. They are, as I think one of the panelists said, they are looking at global markets. And so, if there's a lot of money coming from an adversary at time of war, it's unclear that we can just assume that every commercial actor is going to be on the side of the United States. I mean, it's not like the aircraft model where we can just take over the airlines. I think in order for some of that to happen, we need to take action to make sure that in time, whether it's peacetime or wartime or whatever, we are able to leverage these commercial small sat developments, which means there needs to be support. So we did some interviews as part of some work we were doing, And one thing we heard from a lot of the DoD and government folks is, we'll wait and watch. Let's see them get successful on their own, and then then we'll purchase. We'll be a customer. We'll be a consumer. And I think that's all well and good, but then we have to be prepared for the possibility that these companies may move overseas. They may have enough customers overseas that their products are customized to other countries' needs. And it doesn't have to be anything nefarious either. I mean, let's say if DIUx has customers in Norway, a lot of what their algorithms are going to be focused on water-based analysis as opposed to land-based analysis. And I think we would need to be okay with that. So I guess my bottom line is that in order for this resiliency to be planned and for it to be real, we need to make plans. We need to figure out how it's going to happen and not just assume that, oh, well, we have a commercial sector. They have small sats. We're all set.
So, Aaron, I'm realizing I put you again at the end. Next question, I'll start at your end.
All right.
Well, what's left to say?
Well, I was just going to add that I think the points are made that we're not looking at replacing exquisite systems, but rather complementing and augmenting them. That's an important point to reemphasize. And I think as the government looks at opportunities to leverage commercial endeavors, technologies, and programs and capabilities, the question that many of our sponsors are looking at is, do we want to develop and source from them an integrated solution or a dedicated solution? Meaning, do we want to buy data from them, or do we want to stand up our own duplicative system that leverages product line capabilities of those? And that really drives to a point of a business model of the companies. And so we're seeing both an appetite early stage of these startup companies to want to work with the government and government sponsors to do pathfinders and get their boots on the ground. But really, their venture cap backers in many cases are looking at markets that are well beyond that of a very stable government market. And so we see a divergence occurring down the road. And so how does the government access the commercial market capabilities, but at the same time recognize that there's not necessarily a long-term relationship that may be enjoyed at present? So I think that there's a rising tide here, but there are still questions to be worked out.
And so I'll start at your end then, Aaron. So my last question before we open it up for questions from the audience is, if we want to see the small satellite market succeed this time around, what does the government need to do, or what does the government need to stop doing to help enable this to occur?
Well, that's a great question, and I hate to start with something as dry as mission assurance or risk posture and that sort of thing, but when we talk about trying to embrace all of the good aspects and momentum and resources being drawn into the commercial sector for government purposes, we have to recognize that there is going to be some lessons learned and crawl, walk, run, and experiences that may not be successful off the gate. And so part of that is tempering expectations and learning to understand that the risk posture is a little bit atypical in that respect. At the same time, engaging the companies and communicating expectations, perhaps providing resources to help make them successful are ways in which that risk can be mitigated in some respects. But I think the dialogue needs to be not just give me what you got, but also let's try to strike some common grounds to how we can work together is going to be essential.
Bhavya, thoughts?
I like lists, so I'll give you a list. What does the government need to do? I mean, I think one thing the government has to do is fund upstream R&D. So, emerging areas of technology, optical communication. I mean, absolutely, there needs to be some government investment in it. Technologies which are not of interest to commercial actors. Active debris removal. I mean, I think that's something the government needs to invest in. So that's the first area, R&D for upstream activities. Second one, risk reduction. I mean, there's all these technologies that we have. It would be useful for the government to participate in as either a public-private partnership or be leaders to figure out how to take it to a level where we can, they are routine. Third ones, and actually it's a boring one, but if you interview industry, that's the first thing that they tell us is industrial commons. We want databases. We want to know what components work. We want to know what is the history of a particular system. We want to know. We want testing facilities. We want thermal vacuum chambers, that sort of thing. So the government has a role there. The next one is supporting standards. Whether it's a CubeSat standard or some other sort of small sat approach. I think this one may be a little bit controversial, but something to think about, subsidizing launch. Especially if there's emerging new technologies that won't get venture funding or that sort of thing. Next one, and I think that's the one we talk about a lot, just being a customer. And DoD and NGA and NOAA and NASA are all doing a good job there trying to purchase and supporting industry by being a customer. And last but not least is regulation. And by that I don't mean create regulation or impose regulation, but just think about what are the sorts of things we need to think about. What do we need to do to make sure we have safe on orbit activity, or what should be the standards for image resolution. And again, maybe there isn't any, but we need to just think about it. That's the role of the government, I mean.
Yeah, so one of the things you mentioned there is, the government being a customer and buying some of the services or capabilities that are being provided. So, Colonel Butow, what is DIUx doing to be a good customer?
Yeah, we're pretty opinionated on this. So we think the government needs to be an outstanding anchor customer. So for a lot of these are a lot of emerging startups, new ventures, and we don't fund 100% of anything. When we don't put out a laundry list of requirements, we put out a problem statement, and the companies respond by saying, here's how our commercial solution can solve your problem. And by doing that, we're not reinventing these companies by just doing business with them, right? So we test that model of using their commercial solutions to solve our problems, and so that's really good. But when they have difficulties, which they invariably do, we have a wide range of resources at our disposal, so we can bring technical assistance to them. So I think, we don't always have to do the government subsidy, although I think that's something more on the launch side. But a lot of times, the best assistance we can do is just give the technical assistance, or steer them away from doing things maybe we've got some experience in the past. And I will echo one other thing, which is very important, is that we have to be on the leading edge of the policy and regulation, because a lot of the policies and regulations that are there were crafted decades ago, and we've made some decisions in the past that have impeded the evolution of commercial space industries in the United States, when the Europeans, the Canadians, and the Japanese did not. So we have to be competitive, as an industrial nation. So,
Bill, what are your thoughts?
Well, yeah, no, my thoughts are I'm feeling really sorry for Aaron for the last two rounds. So that was a very, very complete answer. I agree with absolutely everything that was said, and the only thing that I would perhaps embellish is that traditionally, right, the role of the government should be to help create the appropriate environment or ecosystem for the private sector to succeed. And in addition to the basic science, which tends to not be supported by industry, the regulatory environment, the legal liability issues and all are absolutely critical. And I know that the legislative branch is now starting to look at this very seriously. I know the House Science, Technology, and Space Committee just dropped a bill on, I think it was called the Space Commerce Free Enterprise Market Act. It's a catchy name. And in that, they actually cover a lot of the basic ideas that have been discussed. It's actually a very, I think, forward-leaning draft bill. And but I think that that's, again, an important role for the government to help not create wealth, but to create the environment by which industry can create wealth and capability.
Okay, so with that, I want to open it up to questions from the audience. So if you have a question, please raise your hand and we'll bring a microphone over to you. So let's start over here. And please state your name, let us know where you're from.
Steve Welby, I'm representing myself. The chart that you put up at the beginning, Todd, you expressed your general skepticism, as you often do, about kind of hockey puck curves like that. But much of the growth people are talking about assumes the economies of scale and risk and cost that are going to drive this. I'm curious from the panel, What do you see in the near term over the next 12, 24, 36 months? Are there indicators that we're likely to see that are going to tell us whether we're going to see this explosion or not? What are the early warnings of success or failure in this emerging market? Thanks.
Thoughts?
A couple interesting markers that I've seen as it pertains to constellations like OneWeb, who have looking to launch 1,000 satellites plus, is how do you achieve a price point that makes that profitable and economical, and that trickle down effect of having expectations of trying to build a $500,000 satellite delivered to launch vehicles is the supplier chain that are trying to feed in that. And so we're seeing evidence of suppliers that would traditionally support star trackers that may have been $500,000 now selling them for $5,000. And so we are seeing people trying to innovate and work within, of course, large-scale contracts to support these large-scale production activities. And then correspondingly, how do you bring together those pieces? Well, as large investments in the upfront and a rate to develop automation, integrated test, and production line assemblies to support those kinds of activities. And it's that's the only way they can achieve the throughput to create 1,000 satellites within a meaningful period of time. And so it's a pretty large what do you call it, sphere of influence that's being touched by these large programs.
I guess the one I would add is NOAA has just given out its first license for an on-orbit operator. So again, it's a positive sign. Again, it's not something that's going to put 1,000 satellites up in LEO, or GEO, but it's a sign.
I'm going to throw my weight behind it. It's really going to come down to the launch, a small launch, because the commercial small sats are really only become interesting, I think, at scale, and you can put a lot of them up, but they have to be in the right orbits. Rideshare, my opinion is that rideshare is incompatible with commercial satellite constellation employment. You can't have this random way of just throwing stuff out. And on a DoD side, we wouldn't be very good stewards of space if we're paying to put a lot of small things in unpredictable orbits. So it's imperative that we get a small launch, and that every payload can be a primary payload. In other words, we have to be able to get every small satellite to its mission design orbit. And that's not a small feat. So, but there's a lot that we can do in the middle ground. But I do think that the success of this small commercial satellites is really going to be tied very tightly with launch. You can't have a constellation if they're all sitting in the barn waiting to go up.
Already said it all. Okay. Here, next question up front.
Thank you. Sandra Irwin, reporter with Real Clear Defense. I had a question for the Colonel. In your portfolio at DIUx, can you talk about some of the contracts that have been awarded under your portfolio? And going forward, what kinds of companies are you talking to? There's a lot of startups. Can you say a little bit about what the environment is like right now? Thanks.
Right. So one of our prime directives is that we always allow the commercial companies to decide when they want to announce that they're doing work with us, and it's not for all the reasons you think. Actually, a good portion of the companies that we work with are still in stealth mode, which means that they're doing developmentals, they're trying to get their strategic advantage, but they don't want everybody to know what's going on, and it's interesting to see. We've developed a good rapport and leverage a lot of the relationships established by the labs with the venture community. So that's how we get access to a lot of these emerging companies. There's two that I know that are at least discussed publicly. I think one is Capella Space, and another one Orbital Insight. So there's an example of a small satellite company and a data analytics company. And the interesting thing there is that they're doing all the things that have been talked about on the panel, moving, feverishly towards this objective. Again, we only put in a small amount of money, and they're developing these commercial capabilities for not just a U.S. market, for a global market. So because we have this contractual agreement with them, actually, and that's actually it's what we do our work under other transaction authority, which is a little exception to the federal acquisition rule. So we have a lot of flexibility, and what will happen is, and we do a competitive award, so it's not just those two companies, but we, over the course of the work, which will be 18 to 24 months, we follow milestones. We can continue on that course of work. We can rescope it. We might pivot if they were focusing on, let's say, the energy sector, and they move towards maritime. As long as it's consistent with what our end state is, we can pivot with them. Or to coin a very important phrase when we were set up, is the fail forward fast. We can experiment with the company, but if 6 months or a year into it, it just doesn't look like we're a good match, we can bow out, and they're still a commercial company, which is really great, because we don't want to create defense contractors. The idea is we want non-traditional solutions, and if it works at the end of this, the Congress has allowed us to be able to go to a sole source contract or to a production contract without having to recompete, as long as we do a competitive solicitation at the front end of this whole deal. So it's actually a lot of fun.
All right. Next question, right here. Bringing a mic around. Sorry.
Hi, I'm Pat Hose with Janes. Colonel, question for the Colonel. Can you talk a little more about this battery experiment? Maybe give us a timeline and a goal, and perhaps are you experimenting with new battery technologies that aren't commonly used right now?
So what it is our portfolios and our focus, we usually like to, we don't invent anything like the labs do. We actually look at where the hot, parts of the commercial sector are. And with the recent advent of electric vehicles, there's like big money going on to find, better alternatives to lithium-ion technology. We're really pretty much just a little bit shy of the theoretical limit. But just like everything else we're looking at, there's these convergences of different technologies and metamaterials and our ability to manipulate things at the nanoscale. There's some great things going on that they're not quite in the commercial sector yet, but they're kind of at that tipping point. So that's why it's so invaluable that we, our chief scientist at DIUx, Dr. Bernadette Johnson, she's an alum of MIT Lincoln Labs. And so our Boston office is a half a mile from MIT. We're about a little more than a half a mile from SRI out in Silicon Valley. But I can go to coffee. I can get together with those guys, and they give us great ideas about who's doing stuff in the space. There's companies that spin out of the labs. And we like to keep track of those folks and what they're doing. So without getting into proprietary stuff, there's just a lot of interesting activity in this environment. And the wonderful thing is the companies that are doing this stuff are all wanting to produce cells that are about the size of a lithium ion cell. So when we talk to our satellite providers or our folks working on drones or anything else that are interested in battery technology, if it's cheap and they're able to take higher risk, we can bring these technologies in and test them. And for the duty cycle, to get these duty cycles from a double or triple where they're at right now, that's the equivalent of having a second or third satellite that you would have to launch otherwise. So it's really neat.
What's a duty cycle?
So a duty cycle, well, actually, I'm gonna defer this down to our APL guy, because I know he can give you a better answer on it than me.
Duty cycle, the percentage of time that a payload or some device may be on is a function of an orbit or a rev or a day. While I have the mic, I just want to add one clarifying point, which is exciting to see all these new technologies coming forward, advanced manufacturing techniques, new battery technologies, mechanisms, things that really enable dramatic improvements in capability. The challenge we're seeing as the spacecraft and developer side, the payload developer side, the satellite developer side is really accelerating, is how do we then bring that back to the launch side and say, okay, this isn't a risk, it is a new battery you've never seen before, but trust us, it's not going to have a Samsung event, it's going to be okay. And other mechanisms, things of that nature. So there's it's an interesting, a bit of a strain gauge that's basically pulling back some of the advances because these people also want to launch their satellites. And so how do you verify that these will perform as expected? So it's an interesting choke system in some respects, but exciting.
Question right here.
Hi, I'm Travis Cottom from SAIC, and my question is referring to the 25-year orbital debris mitigation guidelines. So we have thousands of proposed small sats, a lot of which only will operate for a couple of years. And a lot of these companies want to have a high refresh rate so that they don't lose capabilities. Do you think that we need to start thinking about revisiting that timeline of 25 years, bringing it down, and when do you think that would be the right time to do so?
Who wants to take this one first? It's a lot of objects to be thrown up in space if you look at that chart.
We'll start in the middle since, I mean, we're very conscious about this, and I think it's unconscionable that we have CubeSats that operate for, a few months and they're in, 25-year or more orbits. And but there's lots of good solutions to that. And I think what's really important is, being good stewards of space. And if we're helping to, if the government's going to do business with these companies, and we're going to be that outstanding anchor customer, well, we can set some rules of the road as well. There are technologies for deorbiting these things. And that are fairly mature. We don't have to put them in really high orbits. A lot of these sensors will actually perform much better in lower orbits than the higher ones. But it's something that it takes a lot of careful planning. We shouldn't be putting large numbers of these CubeSats in the orbital altitudes with our manned spaceflight systems. And there's other good solutions using platforms and whatnot. But our intent is to try to spur the small launch community so that we have the ability to put all these payloads exactly where they need to be and not by happenstance.
Bhavya?
So to your point, yes, the 25-year guideline was arbitrary to begin with, and certainly we should have started yesterday to look at it again. So your point taken, but I just wanted to add a couple things. That the things to worry about, of course, we don't want debris in space, but the things you worry about are the things you worry about first are things like rocket bodies and other bigger things that are much more problematic before getting to the CubeSat. Small sat issue. Again, not to say that they should be irresponsible behavior, but we need to. So there's a study by NASA which is public, which really does look at debris by size and where So you need to be looking at the very small things and the very big things before you get to the 10 centimeter and above, 10 to 100 centimeters. So that's it. That was just a point to make. And then again, in addition to guidelines, there is. And there's other solutions, active debris removal. There's the issue of propulsion. I mean, right now, most CubeSats, no CubeSats have propulsion. And there's several companies and several organizations working on CubeSat and small sat propulsion. Those things are important to continue to focus on because you could maneuver them out of the way. So lots of things need to happen simultaneously, including looking at the debris mitigation guidelines.
I'll just offer that present day with the optic now shifting to very good stewardship of space, you're not going to launch on a U.S. launch vehicle without some mitigation and deorbit plan that shows a timely deorbit, so you're not going to be resident for infinity. The question that was raised, which is how do you get down beyond your mission lifetime, and there's, as noted, several techniques for passive deorbit as well as other things that don't involve propulsion. So I think there's a much greater focus on being, like I said, good stewards of space. And companies that are trying to go to space and bring satellites to orbit, like NanoRex to station, others going to ride shares, are trying to be very proactive in engaging NASA and others in those safety concerns.
And I would also just point out that a lot of these mega satellite constellations that we're talking about, they're going to have a vested interest because they want to keep using those same orbits for their follow-on constellations. So they're going to have an interest in making sure they don't create debris for themselves.
One rate tack, the liability never goes away. So if they're going to get, if you're one of these large venture firms, or or if you're on the board of directors of these companies, you're going to be paying attention to the fact that you don't want something with your brand name up there becoming a collision hazard for something else at a later date.
All right, other questions? We have one back over here on the right-hand side.
Hi there, Amy Camo from Bryce Space and Technology. So in order to have this spike in the small satellite industry, they have to be physically built and operated. Do you foresee any special pop-up companies that could come in and be a specific satellite manufacturer? Or do you foresee that the traditional bigger companies will take on these contracts and kind of pass on the buck to smaller companies that are already there?
All right. Who's going to build all these small sats?
So wait, so the question is, are there smaller manufacturers of small sats? Sorry, can you clarify? Yeah? Okay.
Do you believe that the traditional commercial companies that are already out on the market now, are they going to be the ones that are building the small sats in the future, or are smaller companies that are going to kind of pop up in the next few years, are they going to be the ones that specialize in these specific applications?
So it isn't smaller companies that will pop up. They already have. So a lot of the really interesting work is being done by the smaller companies. So there's a company called NovaWorks, which is developing sort of a Lego style satellite, which you can just build up. There's other companies like DIUx System, which are developing completely new approaches to low cost and mass manufacturing of satellites. And there's a huge list of companies doing very interesting different ways of building satellites. But just to add to that, I don't think the big companies are sitting around. I mean, they are learning their lessons. They will be building. They will be catching up. So it'll be a very exciting ecosystem of a lot of innovation.
Well, and Aaron, what are you seeing down at the component level? Are there opportunities for new companies to get in? Like you said, the example of a star tracker before. Could a company get in that just specializes in star trackers that are very low cost for small sats?
That's a good question. I think if you looked at the state of the industry 10 years ago, it was a fairly blank slate, very limited suppliers, whereas now you've got a huge spaghetti mess of companies that are developing individual subsystem components that are also servicing their own satellite system needs. Some of those systems are also providing vertical integration for commercial offerings as well as product lines to industry. And so, yes, there are opportunities for new companies to get into the market and have new discriminators at price points or technologies. And I think that many of the companies that are offering the systems don't have a number of missions under their belt. So while they have perhaps a backlog of orders, there is still time to demonstrate performance in orbit and capture new markets. So I think there's opportunities out there. I will say that the larger traditional aerospace companies are looking at the very small companies that started organically and saying, your price points don't make sense to us. We can't make money building $1 million CubeSats or something of that nature. Maybe if you were to have an order that was 1,000 satellites, we could consider that. And so we're seeing lots of partnerships, investments, and certainly a watchful eyes of the Lockheeds and Boeings of the small companies as to where they might evolve. So I think it's a fairly fluid market right now where there are opportunities, but some things are starting to coalesce.
Yeah, what I would add to that is, short answer is both. Right, and I think I agree with both what Bobby said and Aaron said, is small companies are popping up. They exist. There's a sort of within Silicon Valley and other places, there's sort of this almost bubble forming. Traditional companies are watching, But I think one of the other things that's really exciting is beyond even the traditional small sat or the bus manufacturers and the launch vehicles, you're also seeing a sort of a secondary market of companies now starting to look at the data analysis of the products that would be coming out. We're also, SRI just spun out a company that deals with space tracking for particularly to tie into the commercial sector so that you could actually get a very accurate ephemeris of both where you are as well as where everything else in the neighborhood is. And so there, you're going to see this whole secondary and tertiary markets coming up as well.
You know, it's the government has an insatiable appetite for data, but it's unusable if we don't know the quality standards of the things that we're using to make these insights. And the challenge when you're dealing with non-traditionals, a lot of the new startup companies, is they can produce one or two, but can they produce 50, 100, or 1,000? And the good news there is that a lot of the money that goes into these companies is from investors who do a lot of microelectronics, mobile tech and things like that. And so the board of directors and the investors in those companies are going to force them to think outside the box. And Space Systems L'Oreal is a great example of a company in the San Francisco Bay Area that does a lot of traditional defense, but they're doing a lot more production type of things. And I think going back to that industrial resiliency I talked about earlier, I think that'd be a great way to build industrial resiliency is encourage some of our traditional companies to work on this, and that's another pathway for some of the technical advances to make it into our defense industrial base.
Yeah, Colonel, just as a comment, is that it'll be very interesting to see how Planet proceeds, given now they've got a mixture of the vertical Dove-developed systems with a SSL Terabella product in-house. So I agree.
Yeah.
Okay, well, I see we're running out of time here, so we're going to take a quick break, and then we'll pick up with our next panel looking at small launch. So please join me in thanking the panelists. Thank you.